Hi, my name is Pau Gallego, and today I'm going to explain how my code works using backtracking. First of all, we need a function that does the Gauss elimination, and this function has to return a different type. What are these types? Those types are different matrices types. For example, the compatible determinate, the compatible indeterminate, and the incompatible matrix. So my code uh, reads the matrix and knows which one of them is. So how does my function do that? First of all, for each column k up to the minimum between the n and m that are the rows and the columns, it searches for the largest absolute value in column k from row k down and uses that row as the pivot. In here, if the pivot is nearly to 0, then the system might be indeterminate or inconsistent. Otherwise, it uses the pivot row to eliminate all entries below in that column. So, how does that really work? Our function detects inconsistent rows, that are the ones that are all zeros, and the column V that is the result is another number. So if the pivot is effectively 0, the code checks is the entire row A approximately to 0, and if is it the corresponding V, that the result of the row, also 0. There are two possibilities: the 0 row in A and the 0 in B. This equation gives no new information. The system may have infinitely many solutions, so the code returns compatible indeterminate. But if the matrix A has an entire row of zeros, but in column B there are no zeros, this means the system contains an equation like 0 equals to C that may be 5, 6, or any other number, which is impossible. The system is incompatible, so the code returns incompatible. After that, my code continues doing the elimination, so rows if it's necessary, and that's the elimination. So once the elimination is finished, the code scans the diagonal entries in here. If any diagonal is effectively 0, it means the corresponding variable does not have a pivot. A system without pivots in all variable columns cannot have a unique solution. The code classifies it as a compatible indeterminate, and if all diagonal entries in the first n rows are non-zero, the system has a pivot in every variable column and is compatible determinate. So, how the back substitution works? This function, assuming elimination produces an upper triangular system, back substitution sums the system from bottom to top using that formula, and the code does exactly what that formula has to do. So, and this is the standard algorithm used everywhere in numerical linear algebra. So now let's see what happened with this code. Okay, this is our main when we call the function to do the back substitution and to the Gauss elimination if it's necessary. Okay, and now let's prove it. Should be compatible determinate, and it should do the back substitution, the backtracking. Sorry, and it does. And our code, but for that we have to change those parameters to 4. If not, it will not work. And you can see it in here, the system is compatible determinate, and it shows us the solutions. And the same way works with the compatible indeterminate and incompatible. Sorry. So let's check it. As you can see, the system is compatible indeterminate, and it didn't show the solutions because it does not enter the backtracking. And now we can see it for let's see, and the system is incompatible. It has no solution. And that's how my code works. Thanks for listening.